In the triangle in the diagram, AB is congruent to AC. And we're told that the measurement of angle B is 40 degrees. We're looking for the measurement of angle A. Pause the video and see if you can find the measurement of angle A. You might be thinking, in order to find the measurement of angle A, first you can find the measurement of angle C. Since this triangle has two equal sides, it's an isosceles triangle and it's going to also have two equal angles. This angle, angle C, is also going to be 40 degrees, just like angle B. And that leaves angle A to be 100 degrees because all three angles of any triangle need to add up to 180 degrees. What we're using here in order to find the missing angle measurements is a theorem called the base angle theorem. What the base angle theorem says is that if we have a triangle that has two congruent sides, so an isosceles triangle, the angles across from the congruent sides are also congruent. Those are the base angles. If a triangle has two congruent sides, the angles opposite those sides will also be congruent. That's what goes in the blank. Here we have another example, and we're given triangle PQR. We're told in the question that the measurement of angle Q is equal to the measurement of angle R. So those two angles are congruent to each other. And we're told that PQ is 5x minus 7 and PR is 2x plus 11. The first question says to find the length of PR. Pause the video and see if you can find the length of PR. You might be thinking to find the length of PR by setting 5x minus 7 equal to 2x plus 11 in order to find the x value. You can do that because this triangle does have two equal sides. But in the question, it doesn't tell us that the triangle is isosceles, and it doesn't tell us that PR is congruent to PQ. We're figuring that out from the angle measurements. Since angle Q and angle R are equal to each other, we're concluding that the sides PR and PQ should be congruent. And that's the converse of the base angle theorem. If we have a triangle that has two equal angles, the sides opposite from those equal angles will have congruent or equal measures. It's called the converse of the base angle theorem because it's the base angle theorem in reverse. The base angle theorem was starting off with information about the sides, and we were drawing a conclusion about the angles. The converse of the base angle theorem starts off with information about the angles, and we use it to draw a conclusion about the opposite sides. Both the base angle theorem and its converse are specifically for isosceles triangles. I'm going to fill in the blank here. If a triangle has two congruent angles, the sides opposite those angles will also be congruent. We take a second and we finish solving over here for x. We have x is equal to 6. And then if we plug in, we can find the length of PR. And we have that the length is 23. The next question says, the perimeter of the triangle is 76. Find QR. We can plug in our x value into PQ first because we have the expression 5x minus 7. 5 times 6 is 30. Minus 7 is also 23. And that makes sense because we already concluded that these two sides of the triangle should be equal to each other. They were opposite from the congruent angles. Now the perimeter of the triangle is 76, so all three sides together have to make 76. These two sides are 23, so 23 plus 23 is 46. Now we just need to figure out what the last side is to make 76, and that's 30. The last part of the question says to explain why angle P is not 60 degrees. If we think about what kind of triangles have 60-degree angles, that is an equilateral triangle because in equilateral triangles, all three sides are equal. So that means all three angles are equal because angles opposite from congruent sides have to be congruent. That's the converse of the base angle theorem. So if we know that an equilateral triangle has all 60-degree angles, triangle PQR is not an equilateral triangle. It only has two equal sides, so it's an isosceles triangle. So we cannot conclude that angle P is 60 degrees. If this were to be an equilateral triangle, then it would be 60 degrees. Now we're going to do some proofs that use the base angle theorem and the converse base angle theorem. I recommend that you pause the video and you draw the diagram on a piece of paper so that way you can mark it. Here we're given isosceles triangles ABC and ADC, and they have a common base AC. And our goal is to prove that angle BAD, so this whole angle over here, this angle that is this angle from triangle ABC and this angle from triangle ADC together, is congruent to angle BCD. Notice how angle BCD is also a combination of the two angles from the triangles ABC and ACD. Now, we might automatically think that we need to prove the two triangles congruent to each other. But if we think about that for a second, triangle ADC is clearly much larger than triangle ABC. So we're going to have a really hard time proving them congruent because they're probably not going to be congruent to each other. Also, we know the triangles are isosceles, so that means that they each have two equal sides. Just going to mark that in the diagram. And we do have the shared side AC. So you might be thinking the triangles are congruent by SSS. But when we have triangles that are congruent by SSS, three pairs of sides between the two triangles need to be congruent to each other. But here, the congruent sides are not from each of the two triangles. They're on the same triangle, the same isosceles triangle. So we don't know the relationship between the sides of the two triangles. So this is not SSS. Let me erase this. And now we can think about how to get the angles that we need. We do have isosceles triangles, so let's think about what else we know about isosceles triangles. Not only do they have two equal sides, but they also have two equal angles, opposite from the congruent sides. So in triangle ABC, the two equal angles would be here and here. And in triangle ADC, the two equal angles would be here and here. So now we know that the pieces of each of the angles, BAD and BCD, are congruent to each other. So if we have the pieces of the angle and we need to put them together to make the whole angle, that's sounding like the addition postulate, if we have to put parts together to make a whole. So if we add the purple and the blue angle here, and the purple and the blue angle here, we'll get the whole yellow angles, which are the ones that we need to prove congruent. I'm going to pause the video and write the proof up. I recommend that you pause the video as well and try to write the proof on your own. And here we have the full written up proof. It is only 5 steps, including the givens. Remember to state in your proof that the sides of the isosceles triangles are equal to each other, like I have in step number 2. I know that we knew the triangles were isosceles from the givens, but if we want to mark AB congruent to BC and AD congruent to DC in our proof, in our diagram, and we want to use that to draw conclusions, then it also has to be in our proof. And then notice in step 3, I put the conclusion that we drew about the purple angles and the blue angles due to the base angle theorem. If two sides of a triangle are congruent, the angles opposite those sides are also congruent. And then I show that the addition here, the purple plus the blue angle gives the whole big yellow angle. The purple plus the blue angle here gives the whole big yellow angle. So where I'm actually adding the angles, that's the addition postulate. And then this plus this is the whole yellow angle. This plus this is the whole yellow angle. That's substitution. We're going to do another proof. So we're given that CA is congruent to CB. So I'm going to mark that in the diagram. And we're also given that angle PAB, so that's this angle right here, is congruent to angle PBA. That's right over here as well. And I do recommend that you pause the video and draw the diagram on a separate piece of paper. That way you get yourself set up and you can mark it and try it out for yourself as well. And our goal is to prove that triangle EPA is congruent to triangle DPB. There's lots of triangles in this diagram, so I'm going to highlight the two triangles that we're proving congruent to each other here in this proof. And it's the two in yellow. And they're not the overlapping ones, they're just two separate small triangles. So let's think about what conclusions we can draw. So I'm going to go back to my first given. And from my first given, I know that CA is congruent to CB. So that means the whole big triangle, CAB, I just redrew the big triangle without all the stuff inside, without the smaller triangles. And that means the whole big triangle is isosceles. And we know that if we have a triangle with two equal sides, not only does it have two equal sides, but it also has two equal angles. And those angles are located opposite from the congruent sides. So I'm going to mark that in the big diagram as well. The two base angles of the big isosceles triangle are congruent to each other. We also know that the two red angles, PAB and PBA, are congruent to each other from the givens. So that means this triangle here, APB, is an isosceles triangle as well. Because remember, the converse of the base angle theorem says if a triangle has two congruent angles, the sides opposite those angles also have to be congruent. So in triangle PAB, the sides opposite the congruent angles are congruent. And that gives us a side, PA and PB, to work with in the yellow triangles that we need to prove congruent. Since we have information about this whole green angle and the red part of that angle, if we use subtraction, we can get the piece of the angle that's actually in the yellow triangles, and then we can use that to prove them congruent. And then the last thing I'm going to need here is we do have vertical angles, which are really nice because they're always congruent to each other. Remember that whenever we have intersecting lines, whenever we have a letter X, we have those congruent vertical angles formed by the intersecting lines. That's a really bad marking. Let me fix that. Okay. This is congruent to this because they're vertical angles. So now we have everything we need to prove the yellow triangle is congruent. That's going to be angle, side, angle. So I'm going to pause the video and write up the proof as well. Try to make sure that everything that we marked in the diagram ends up in your proof. Here is the full written up proof. Notice the difference in the reasons for step 2 and step 5. Step 2 is using the base angle theorem because we were starting with the information that the sides of the big triangle were congruent, and we were drawing the conclusion about its base angles, the opposite angles from the sides. So notice how that's worded. If two sides of a triangle are congruent, the angles opposite are also congruent. Down here in step number 5, we have the information from the givens about the angles inside the smaller triangle APB. And from knowing the angles were congruent, we were concluding that the opposite sides were congruent. So that's the converse of the base angle theorem. And notice how that's worded differently in the proof. If two angles of a triangle are congruent, the sides opposite are also congruent. So that's why you should write out which theorem you're using instead of just writing base angle theorem or converse base angle theorem. If you accidentally wrote converse base angle theorem here or base angle theorem here, that would be marked incorrect if you were taking a test or the Regents exam. It's better to write it out. If you're starting with angles and you're concluding about the opposite sides, write that. If you're starting with sides and you're concluding about the opposite angles, write that. We're going to do one more proof on this video. Once again, I recommend that you pause the video and you draw the diagram so that way you can mark it. So we're given that GH is congruent to EH. So I'm going to mark that over here. And already I'm noticing this small triangle GHE is an isosceles triangle. It's got two equal sides, so it's also going to have two equal angles. I don't know if that's going to be important. I didn't get to take a look at the proof statement yet. I'm just going to put that in there just in case it is, and we can always erase it if we don't need it later. And we also have that AE is congruent to GC. So here is AE and here is GC. That's a little hard to see. If we take a look at the first proof statement, we're proving that triangle ADE is congruent to triangle CFG. So those triangles are overlapping, so it's a little hard to see clearly what's going on. So I'm going to color code them. I'm going to make one of them green, and I'll make the other one blue. And I'm also going to draw them separately somewhere else on my paper, and I'm going to relabel them and remark them. And that way we can better see what we're working with in the triangles. That's a D, DAE, and FCG. And I'm just going to mark what we have so far. So we had AE congruent to GC from the givens. That's here and here. And from the original diagram, you might have been thinking that we might have had to use like subtraction or addition postulate, but that's why drawing the triangles separately is very important, because we can actually see that we already have the full sides of the triangle. We don't need to do anything else. We already have those sides, AE and GC. We concluded from the small isosceles triangle that angle 3, which is right over here, is congruent to angle 4, which is right over here, and that gives us another angle to work with. And now we just need another piece of information about the two triangles. Either we're going to need a side or we're going to need an angle. And looking back on the givens, I forgot to mark one of the givens in the diagram. I forgot to mark that angle 1 is congruent to angle 2. And since angle 1 and angle 2 are congruent, and angle 1 and angle 5 are supplementary, and angle 2 and angle 6 are supplementary, angle 5 and angle 6 have to be congruent to each other, because angles supplementary to congruent angles also have to be congruent. For example, if angle 1 and angle 2 are both 50 degrees, these two angles would have to be 180 minus 50 because they're supplementary with the 50-degree angles. So whatever these are, since they're the same, these have to be the same as well to make the 180 degrees. So supplements of congruent angles have to be congruent to each other. And that gives us a second pair of angles that we can use. And now we have that the triangles are congruent by AAS. I'm going to pause the video and write this up so far. You should try to do the same as well in a 2-column proof. And here's the proof written up so far for part A. Notice how before we can say angle 5 is congruent to angle 6, we do need to state that angle 1 and angle 5 are supplementary, and that angle 2 and angle 6 are supplementary, and that's step number 3 here in my proof. And my reason for that is angles that form a linear pair are supplementary. So then we can say angle 5 is congruent to angle 6 because supplements of congruent angles are congruent. Before we can use that theorem, we do need to establish that the angle pairs that we're talking about are supplementary. So that's why step 3 is needed. And then we have AAS. Part B of the proof is to prove that angle A is congruent to angle C. Now that we know the two triangles, ADE and GFC, are congruent to each other, it's just one more step of our proof to say that angle A is congruent to angle C due to CPCTC. If the triangles are already congruent, their corresponding angles also have to be congruent. I'm going to also mark that in the original diagram as well so we can clearly see it in both pictures. So let me put that here. Angle A is congruent to angle C, and that is CPCTC. And then we need to next prove that AB is congruent to BC. So that's back to the original big triangle. So now that we just proved that angle A is congruent to angle C, remember if a triangle has two congruent angles, the sides opposite from those angles also have to be congruent. So since the base angles are congruent of this big triangle ABC, the sides AB and BC also need to be congruent as well. So let me put that into my proof. AB is congruent to BC, and we were starting off with information about the angles. So that's if two angles of a triangle are congruent, the sides opposite are congruent. And now the last part of the proof is to prove that triangle ABC is isosceles, which we already know because we just proved that it has two equal sides. So let's just finish up our proof. Oops, over here. So finishing it up, triangle ABC is isosceles. We already showed that it has the two equal sides AB and BC. A triangle with two congruent sides is isosceles.